So I want to start discussing this experiment of Fermi, which is kind of a fundamental example of the kind of things that can go wrong in quantum field theory. So the Fermi experiment, the Fermi lectures in Chicago describes this experiment. And let me see what he did. I did not read the Chicago lectures, but as reported elsewhere. So he considered an atom on the right beta in an excited state at time 0, and the atom alpha in the ground state at time 0, separated by a distance r. And he said that because of speed of light being c, for times less than r over c, where r is the distance of separation, nothing should happen to alpha. Okay? That was his assumption. Then, so the quantum state at time, as a vector state is given by a state of the atom alpha localized here, state beta localized here, and it's a tensor product of these states, the tensor product of these two states and the photon state. Okay? And the claim is that for time less than r over c, this alpha state will not be changed because of causality. So, what does that mean? So, if chi is a projection, I should write chi. There's some notational problem here. Okay? If chi is like, let's say, I should write the project. Take this chi, and what I wanted to write here is this alpha replaced by the projection operator. So the projection operator on the alpha state, the ground state, times the 1, 1. You don't care what happens in the other states. This projection operator says that alpha is in the ground state, and 1, 1 says I don't do anything to the remaining states. Okay? And if so 1 minus chi is a projection operator to the orthogonal complement. So that will be the projection operator where the left state is anywhere at all. Okay? I don't care where it is, okay? Except that it's not in the ground state. Okay? So this projection operator, if I evolve it for a time exponential IHT, okay, the claim is that when t is less than r over c, this expectation value is 0. That is the assumption. Okay? So this is the projection operator, right, written properly, which I have not written properly, and evolve it for a time t. If time t is less than r over c, this is simply 0. That is the assumption of Fermi. Then, much later, it was pointed out by Hagerfeld that if this assumption is made because of the boundedness of energy below, the alpha state will never get excited. The left state will never get excited for any t whatsoever, or it will get instantaneously excited if causality is completely violated. So something is wrong. That was the assumption of Hagerfeld, not assumption, proof. I'll give you the proof. Okay. So the projection operator, chi is a projection operator I am denoting, where alpha is in the ground state, and the remaining state I don't care. Okay. 1 minus that, the orthogonal projector, where chi is in any excited state, and again I don't care what is happening in the remaining ones. This is the projection operator, and it produces q squared equal to q, because it is a projection operator. So the assumption is this should be small t. If I evolve this exponential minus IHT for small t, t less than r over c, this, then I project on q, I will get 0. Okay? That is the assumption of Fermi, which follows from standard assumptions in quantum field theory. Okay? This is the case. I can also, just for math, accuracy, I can take the projection operator on a on an energy state P. Here, the P is a projection operator where I project the beta state of the photon to some energy against it. The, I evolve this by Q, then I apply expression minus IET and indicate over the measure on E for E positive. E is positive because of the fact that the spectrum of the Hamiltonian is positive. So that's only integration possible. And I look at this, it is CB0. Okay. What is P? P is some projection operator for energy E. Okay. Yes? So there are three different spaces. So take the projection operator for the entire thing. Okay. And evolve. So P can be the total, but energy is positive when you add up the all energies. Okay. So this thing will still be zero. Okay. Now look at this expression. Okay. And then you notice that what you're assuming is that if this is 0 for t less than r over c. So the expectation that the scalar product of this object with any state phi whatsoever is 0 for t less than r over c. So this expression is identically 0 for any vector in the Hilbert space. By this equation, you get this equation. Okay. But if imaginary, so look at this. This is a Fourier transform. What you got here is a pure Fourier transform. So I can imagine analytic. I can imagine that this Fourier transform is a boundary value of this expression. Where I make t a complex variable and go into the imaginary lower half of the imaginary plane. This expression becomes this here. Yeah. So imaginary part of t I am taking to be negative, and then you get here a transform where the imaginary part of t term is a damping factor. Okay. So, and in fact, with some technical assumptions, one proves that this expression, that E is positive, is a holomorphic function in the lower half plane. Okay. This is how asymptoticity is with scattering amplitudes in quantum theory. So this thing is a holomorphic function in T in the lower half. Okay. But this holomorphic function, so the actual expression we are finding is the boundary value of a holomorphic function. The boundary value of a holomorphic function in the lower half plane, and it vanishes in an interval. In the real boundary value vanishes in an interval in the real axis, then it by Schwarz's reflection principle, it vanishes identically for all t. So this is the standard thing in real analytic functions coming from Schwarz's reflection principle. So this happens because of the fact that it's the boundary value of an holomorphic function. It just is identically 0 for all t. Okay. Then, so either the expression, the thing I'm looking at here, is identically 0 for all t. Okay. If the holomorphic, if the energy is this object is either identically 0 or is never 0. Okay. But since we have by assumption it is 0 for t in a small interval on the real axis, in fact it is identically 0. Okay. That means that the atom never, for any t, the atom on the left never gets excited, which clearly is physically wrong. Okay. So this was the assumption of, this is the proof of Hagerfeld much after Fermi. Okay. Fermi, I think, also found this issue, and he did some massaging to get the right answer, okay, and not to have this problem. But it was pointed out by Hagerfeld that this is what will happen, and we noticed that this result is correct in atom already in quantum mechanics. But the proof I have used here uses only the fact that the Hamiltonian is bounded below. Okay? So if you do a quantum mechanical system with the Hamiltonian which is bounded below, you will have this problem. Okay? So what is wrong? This is the question which was Hagerfeld's concluded negatively that yeah. Or if it is already a T equal, so it is not a holomorphic function in T. I don't know how that can happen. Okay. But if I write at the beginning at T equal to 0, that matrix element is not 0, then of course, but there's something wrong with that assumption because the assumption that is not the case. So I should not have bothered about this alternative possibility at all. Okay? It is not possible. I don't see how it can be, how it can happen. So, so this is some problem. We don't know what is happening. Okay? And Hagenfeld, I think, concluded that something is wrong in quantum mechanics, something like that. This is a nice proof okay, that he gave. And much later, about 10 years ago, Buchholz and Ingvason wrote a paper in PRL pointing out where the problem lies. The problem lies in the assumption that the Hilbert space of the three things we are looking at, alpha, beta, and the photon, is a tensor product of three different Hilbert spaces. This is a crucial assumption in the calculation we have done, which allows me to localize the atom alpha on the right, left, the atom beta on the right, and photon separately. We have made this assumption, and this assumption, they pointed out, is not correct in quantum field theory. Okay? So, yes. Nevertheless, so the statement is the following. Split property, that is not necessary. In fact, let me come, okay, to split property will come in my next lecture or something. And so, the problem, even if you have localized observables in alpha, beta, gamma, so suppose even if you have in quantum field theory, three localized observables, alpha, beta, gamma, A alpha, A beta, A gamma, nevertheless, the Hilbert space on A does not factorize. This is the problem, okay? Does not factorize even if the three observables factorize in the sense that they commute. Okay? Here, factorization means commutability, and the statement is that even in this case, this cannot be done. Okay? I am thinking, okay, I'll show you very almost certainly now that there's something called the Risch-Schreier theorem, okay, which also will give the similar result. Okay, and I'm a bit puzzled because if I do quantum mechanics, the calculation I did on the black here is I have not used any property of quantum field theory. I have only used the fact that energy is bounded below. Okay? This is also true in any quantum mechanical system where the Hamilton, say the ground state energy is positive, non-negative, harmonic oscillator, it will work. Okay? So what is different here is that we are not looking at states at a given time. Okay? So we are looking at states on the algebra defined in the interval in time. So we are looking at the algebra of observables is well defined even in time in quantum mechanics. You take some time interval, you can define all operators in that time interval, you get the algebra. Okay? That's the kind of algebra we want to discuss. Okay? So when you do that, even in quantum mechanics, it seems that the Hilbert space will not factorize. So the quantum mechanics, by this calculation, provided the energy is bounded below, seems. I will give the same argument also for the Risch-Schreier theorem. So the implication of this in quantum mechanics, people have not brought this out in quantum mechanics, but I don't see anything wrong with what I'm saying. So that I think is a very interesting statement. So one should explore this further. Okay? So let me show you, before I go on, a very simple example in quantum from quantum mechanics where the Hilbert space will not factorize. Okay? This is the just to see the kind of thing that can happen. Even if you are commuting algebras, they won't factorize in quantum mechanics. Why? Take the uh, take the case of two rigid objects, okay? Commuting rigid objects. Okay? So I'll call the and their algebras. Okay? So rigid object algebra is an algebra of say uh, say group elements in SO3. So I will have two commuting algebras. One I will call SU3 left, then I will call SU3 right. And look SO3 left, SO3 right. And we look at the algebra for this one and that one. And I will assume that the only intersection between them is multiple of the identity, which also is the case in the example of H alpha cross H beta cross H gamma, the previous example, because I can identify the unities in all those things. Because the tensor product I was trying to write for the algebra is a tensor product over complex numbers. So unity in all these algebras are identical. So look at this. Okay? That symbol. What is it? C over complex numbers. So it's a algebra of all formal linear combinations of group elements with complex coefficients. But better still, you take functions on this group and take the complex linear combinations of the functions and their products. So that is for finite groups. You have a multiplication table for group elements. Label them 1, 2, 3, n. Take all complex linear combinations of this labeled element E1, E2, E3, an. Take all complex linear combinations that will have a multiplication coming from the group, and that is your group algebra or that finite group. In the infinite case, G is continuous. So what do I mean by linear combinations? You'll get delta functions. So to avoid that, you can take functions of the group, take the dual of the group, and do the similar construction, and then you get the group algebra. Okay? That is what that is a group algebra for SO3, SU3, and so on, okay? Which is fundamental to write the theory of the character theory for SO3. S for Lie groups, S for the Carson theory for any compact Lie group. That is quite essential. Okay? So that's what I mean by C. The algebra is done by with coefficients in complex numbers. Okay? I could also do the same thing with real numbers, or I could do it with any field. You can consider SO3 for some finite field. Okay? Then the scalar multiples. The scalars are complex numbers. That's it. So, what is the representation? The representation of this object, which is irreducible, is simply L2 of square integral functions on SO3, and I write them as chi bar of G times chi of G, psi bar of G times psi of G, indicated with the Haar measure mu G. Okay? So the left action of a group element will be by G inverse. So UL of G corresponding to the first factor, acting on a psi will be psi G inverse H. Okay? D cosine theta d5 times the third angle of the SOC. Okay? So it is the invariant measure on the group. Okay? So if I take this group element and multiply by G prime, change variables, the Jacobian is 1. Okay? So it is a Haar measure. So that exists for all compact Lie groups, all simple groups, all simple Lie groups. SL2C has that. Okay? It's even more general, but certainly SL2 has an invariant measure. Okay? And we use it all the time. Okay? Without knowing about it, we use it. Poincare group has an invariant measure. Again, DQP or 2P0. Okay? That's what we write. It's invariant under the full Poincare group. Translation is it. So that is called the Haar measure. So G acts on the left by this action and acts on the right by this action. Okay? These are the left and the regular representations of the group. Okay. But the Hilbert space is this Hilbert space, and we can find the basis by expanding it in spherical functions. the D functions of Wigner. And so this is the basis of orthonormal basis in the scalar product, orthogonal basis, the D functions. And you notice that this, I cannot factorize this into one part, one leaving for the first one and the second leaving for the second. There is no factorization of this expansion into two parts, one for the first one and one for the second. There is no way to do it. So this is a very simple example where this cannot be factorized into left Hilbert space and the right Hilbert space. And this happens in the discussion of the rigid rotor in quantum mechanics. Okay? So if you try quantizing the rigid rotor, you will encounter this example. Okay.
It's not obvious to me why. It's not obvious why it's not.
Right? I have not tried the proof, but I know no way of doing it. Okay? I don't know of any way of doing factorizing this into two parts. One which will carry purely the left action, and one carrying purely the right action. I don't know how to do that. These are the 2j plus 1 by 2j plus 1 matrices, which are representations, matrix representations of the group. Okay? So, and can I factorize it into two parts? I would not know how to do it. Okay? I have not tried proof, but I thought about it on and off, what it might be, but there is no, I can't find anything interesting. So if you find a counter example, I welcome it, but I don't think it can be done. So the whole point here is that if you have a quantum theory, okay, where you have locality, and what I want to prove, okay, is that there is no projective pk in the quantum theory. Projecting to a space-time region K, the causal complement of K prime, is not null. So there is no, you cannot find a projection operator in K. It's you project the quantum state or the Hilbert space carrying the observables in H to Pk if the causal complement is not zero, it's not null. Okay? This is the upshot of the important upshot of what I have described to you from Fermi. However, so this really means that there is no way that you can localize states compatibly with causality. Okay? This also is related to the result of Mukunda Sudarshan and some others I told you about relativistic point interactions. They already proved, again by using causality arguments, that already classically the problem appears that you cannot interact relativistic particles, actually make them interact with each other, covariant compatibly with relativity and causality. They proved it long ago. Using the classical mechanical tools, and this is coming up again here. So, but one implication I want to say, this means that there are no localized detectors. Why? Because a detector can be thought of as a localized hyperspace on which the experiments are being conducted, and there is no such localization of the detector because the corresponding projection operator does not exist. Okay? So one cannot think of a localized detector. For example, Unruh writes a localized detector for the Miller waves. I do not know whether it is compatible with principles of quantum field theory. I don't know. Maybe.
Seeing that on the LC observation.
Localized detection is the experiment is presumably measuring some observables in some means or other. So presumably localized detector presumably that is meant by a Hilbert space associated to the detector. And
saying there are no
experimentally.
experiment by doing
It will,
I'm catching the light rays. You're saying there are no localizations. That's let's say for LHC, what does it mean?
Often I do not know. It is like bond localization. What does it mean for physics? Bond localization in quantum mechanics. What does it imply? Bond localization. So it was an interpretation of wave functions as mod psi squared gives the probability density in some point. Right? What is the implication of that statement? So what will this will mean? I think will mean is that the detector states will be necessarily entangled. I think that's what it means. Necessarily entangled with the things you are observing, the corresponding Hilbert. So the state you are getting is not pure. So there will be entanglement entropy of the detector with the whatever is observed. So I think that's what it will mean mathematically. Whether entropy can be measured experimentally, I don't know. I suppose so. I don't know. That's an interesting question also. I don't know. Can you measure entropy? I think that's what it will mean. That you cannot. Yes. So what it will mean is that the state in K prime, the quantum state, okay, we have non-trivial expectation values for observables in K prime and in K, and the answers will give correlations between the states, the observables in K prime and the observables in K. Okay? And that correlation cannot be removed. Okay? That's what it will mean. Okay? So, if there were such a projection operator in each region, you can decouple them. Okay? That cannot be done. That is a statement. So, that is, I think, the meaning that the observables cannot be decoupled. That's what I think it means. Can I test it? I think we test it all the time. But specifically, how do we do it? I think it is coming from entanglement entropy calculation, things of that kind. I agree with you that the entropy is a subsidiary concept, but there will be correlations. So the correlations will come between the two observations. What's happening in the experiment, what is happening in the
should not be able to reproduce one set of data elsewhere. So if I do an experiment in Germany, I get some result, I should not be able to reproduce the same experiment in the same Bangalore.
So, okay, I can see, yes, I'll tell you the problem. Unfortunately or fortunately, it seems like impossible to observe non-commutative algebras. Impossible. Why? So your question is related to the another question. Why can't I say, I declare, if you give me a non-commutative algebra, there's no way I can do an experiment on it. Why? Because suppose angular momentum, and you tell me measure third component angular momentum. But how do I know third component? There's no lab, there's nothing to compare third component. The system only knows algebra. Okay. So if I make an inner automorphism by some unitary element of that algebra, is not commutative, it will start permuting the operators. So, and the relative relations will not be changed at all. Okay. So, when you measure angular momentum, I say I want to measure third component. You make it one answer, I make it another answer. How do I know which is correct? It is impossible. Okay. This has been known for some time. Okay. So, what is the resolution? I kept saying this before. Already, well, this I think was the primary question that Niels Bohr and people like that got faced. They did not say it in their language, but this was their concern. Niels Bohr talked about large quantum numbers where he said some classical algebra emerges. You may remember. And then he said that that's what we are observing. Then at some point, people started talking about collapse of wave packet. I think it's Paul Neumann, maybe. Nobody, nowadays, that people don't talk like that. There is another piece of work which I will talk, which will address the kind of issue you're raising about by Hebb in the 70s, who talked about algebras at infinity. Okay? That is, he proved purely algebraically that there, if you have a non-commutative system, then within that, from that non-commutative system, there is an emergent commutative algebra. Okay? It's a very remarkable proof that there is an emergent commutative algebra from the non-commutative algebra. Okay? And he proved, he actually gave a model where what is happening in this emergent commutative algebra, originally due to Ruel and Landmark, something like that, the definition of that, he made up a system where the emergent commutative algebra is classical, how it will respond to disturbances in the non-commutative algebra. Okay? He actually showed it. And if you accept that you can measure commutative algebras, so classical measurement theory is understood, you can do the measurement and you can tell what's happening in the non-commutative algebra. Okay? This is a very, in my opinion, a very deep paper, and it was revived by Imilsi and Fiorini and Imilsi, where they gave a very clear discussion of Hebb and showed that this can happen due to phase transitions. Okay? In say, first order phase transitions, they proved, they showed, argued that this situation will emerge. The commutative elements being for example, for a ferromagnet, the directions of spin at infinity. So they prove that they form a commutative algebra. And if you accept that you can measure commutative algebras, classical measurement theory, then it will register what is happening in the bulk. Now I find that Fredenhagen's review again talks about the same thing. He also sketches how can this can happen, and he gives a sketch. And just now, recently we have found, I should say, that in all gauge theories, this happens. This is something related, all gauge theories on space-time, which is not compact, it happens. So you have an infinite number of supersymmetrical sectors in all these series, QED, QCD, everything, such that the labels which appear in these models for the phases for the different supersymmetrical sectors form a commutative algebra, which will register what is happening in the bulk. So there's some new things are happening. Okay? So which has still many holes because we don't know whether by measuring, we know measurement theory in classical mechanics. We don't know that, in my opinion. Okay? But do I know how, looking at probabilities of functions, I can tell what is space-time? I don't know. Very likely, if there are enough structures, you can using this Gelfand theorems. Okay? But how it actually happens in detail, I don't know. There must be people who have discussed this, but I don't know. So there's a long thing in between. Prior to your question, there are other questions which are lying open and which certainly are very worthwhile to study, think about at least. It may not get you a position, doctorate position, a postdoc position, but it is worth thinking because they are foundational. Okay? They sort of instruct us on what it is that we are trying to do. Okay? The fact that we don't know answers, that doesn't matter. We don't have to know all the answers at once. Okay? So we can wait. I don't know whether I've answered it, but this is a long talk because I think this is. So the thing I was telling about this dynamics of the boundaries, is related to this issue. Okay. So, yeah, there's a way to produce a very natural dynamics at the boundaries. Okay. Not artificially, it's coming very canonically. Okay. And that will register what is happening in the interior. But it will not change the motion or anything. It will register what is happening in the bulk, say in gravity or whatever it is, and should be able and give some at least some information on what is happening in the bulk Okay. So we should discuss this emergent ideas this piece. So how do I prove it? The proof is due to Rischlider. Okay. So let me tell you what the Rischlider theorem is. Okay. Hart says that when the proof first came, they were very surprised. But if you think about it, it's rather natural. Okay. Now it looks very natural. Okay. So we have vacuum states, and what I want to prove is that I take some compact region K, okay, some bounded region K, and but I don't want the bounded region to be a point. That's all the only requirement. And I take points xi in K. And I consider, let me not worry about mathematical technicalities. I apply phi of x1 up to phi xn on the vacuum. But n is some integer. Okay. And I will go on changing both the points and the integer n all within K. Okay. This is some vector in the Hilbert space. Okay. The theorem of Rischlider says that if I go on doing this for all x's in K, all n, I will get a dense set of vectors in the Hilbert space. So by completion, I get all possible vectors. I can approximate any vector in the Hilbert space by this sequence. How do I prove it? Okay. The proof is remarkably simple to understand. Okay. If take all these vectors, suppose let me consider if there is any vector, this is orthogonal to all these vectors. If this is not spanning the full Hilbert space, but only spans a subspace, there should be at least one vector which is orthogonal to all of them. So there should exist a chi in Hilbert space which fulfills this equation. Okay. But when it is 0, but even though I am varying the x's in the n arbitrarily, I will show you that this equation implies chi is 0. So there is no such vector. This is the proof for the Rischlider theorem. Okay. So how do I prove it? So again, it is coming from the positivity of energy. So I take the phi of x1, and I conjugate it by a translation like this. I can write it as exponential I p dot x1 by 0 exponential minus I p dot x1. They go on doing this, and here I get exponential I p dot x2 by 0 exponential minus I p dot so I get exponential I p dot x1 by 0 exponential minus I p dot x1. But p1 is 0 here, so I should have blocking. So you get a sequence of phases. Okay? So I'm just writing out all the phases here. Okay? So the first one will be a phase. So I'm going to go on inserting complete sets. And insert a complete set in the previous slide. I write a complete set involving the momenta P1, P1, then P2, P2, and so on. And here I get Pn and then I stop. Here Pn, and nothing here. Here already there is a 0. So I'll go on inserting complete sets. Using the completeness of the momentum eigenvectors, and I'll write this down. Okay? And I'll get a bunch of phases here. Okay? The phases are coming by acting with the momentums operated on the T's. So I get this expression here. And I want to look at this expression and organize the phases in a good way. Okay? So the phases, the faces you notice that the faces in the previous slide are dotted into the momenta. I get p1 dot x1, then I get next one will be uh, exponential I p1 minus p1 dot x2, so I get p1 dot x1 minus x2 and so forth, right? By taking the differences. So what I will do is this piece that I am writing by the positive energy momentum are all lying in the forward line code. Okay? In fact, the closure of the flow line code, so they're lying either here or inside this one. Okay? So they are all forward pointing like this. Okay? So if I take a vector in the forward line code and this dot product in the piece, it is non-negative. Okay? Or maybe that the boundary I get zero, but it is in the bulk, it is certainly non-zero. It is certainly positive. So I again do what I did earlier. I take x1 to be a complex variable and make it add a small imaginary part, not small, an imaginary part. Where the psi1 here, that's in the forward vector. So this extra term will go and hit with an I here. So I P1 will hit. So I get expression minus P1 dot psi1. Then here I get there's some sign change. Don't worry about that. And they are just to make sure that they get a damping factor. They are adjusted so that the imaginary parts, the exponential damping factor are always positive. So I go into the correct direction in the side in the x the coordinate plane, and you'll find that if I have the size non-negative, I end up by saying that the equation which I was writing before, this equation, this object here, when I make this excess imaginary and go in the right code direction, I will find that this is a holomorphic function. So it's a holomorphic function in tubes. Okay? The tubes being this then product of all these light cones in which I am putting the size. Okay? So it's a holomorphic function in a tubular domain. Then just like I proved the Hegel theorem, there's a theorem called the edge of the wedge theorem, but never mind. Okay. By similar argument to that one, because this equation is what I want to starting assumption is this one, and I am now telling you that if I go with the excess in the imaginary direction in some tubular domain, this object is holomorphic, but then it vanishes for the real section. Then again by identity continuation, it vanishes identically. Okay. So this is the proof. This is the proof. The technical aspect of the proof is to prove to extend the Short's principle to these tubular domains. It's called the edge of the wedge theorem. Brahman, Ermin, third part. Three people proved it. It is not a trivial proof. The Bogoliubov had it already, and it is described in his book. You will see that the proof is by no means true. In fact, Bogoliubov has written a whole book on the mathematical requirements for quantum field theory. So, he doesn't prove the proof he has written now is incomplete. That's why he gets away with it. And he proves it coordinate by coordinate. Okay? That doesn't mean joint holomorphicity. Okay? And you can't infer holomorphicity in the sense of several complex variables. We are involved in several complex variables. So the properties of several complex variables are enormously more complicated than is the case for single ones. So what he has done is prove by one, okay, following the advice of Longo. But if you look at the original proofs, they are involved in proving joint analyticity in all the complex variables together. That is a different game. Okay? And that involves this, what they call edge of the wedge theorem. Okay? I don't know the proof of that theorem. Okay? I come across it many times, but I don't know the proof of that theorem. But one is, what is it? Obdurate. I will study, you can study. It is in Bogoliubov, Todorov, and so forth. That book, which you can download. Okay? Weidmann might have a book. Okay? Weidmann might have a book. Theorem. Yeah. It is not an easy theorem. Okay? So, in fact, it is used in proving CPT theorem by Yost. Okay? Yeah. So, Yost has proved in Bogolyubov. Bogolyubov had all this. Okay? And this was pointed out to me in my discussion with Sasha Pinzul. Okay? And then I looked, and that is true. But see, it's okay. Which's proof is satisfactory for us. Okay? So note that proving things one by one complex variable, one complex variable is okay for us. Okay? But see, several complex variables, they have a natural domain of holomorphicity. You can't do whatever you like. For example, how do they?
Always showing the analysis. It has never included analysis in several complex.
No.
One complex.
Yes. One by one he proved. But one by one is the same as short principle. You can do that. That's a much easier proof. If you are happy, one is happy with that, fine. But it is not a real proof.
What he does is like initially he shifts one variable. So you take the reason that k that you were talking about, and he takes the point that last one is exit outside k to all windows the point. Then he takes 2 points simultaneously, not just one. Right? And he does it for repeatedly for many points. So I think that's a joint probability that you are not joint evidence.
Maybe. As I say, I don't have a control. I was trying to remember the nice example of what will happen with several complex variables. Okay? So in several complex variables, if you tell me, for example, that is Z1, Z2, you say Z2 equal to 0, Z1 is holomorphic in some domain. Okay? That is not a natural domain of holomorphic for the function. Because I can take this Z1 and lift it. Okay? So imagine Z1 going up. I can take this and lift the region. So it becomes immediately a tubular region.
Does see that take Z1 and do you're showing animals Z1. That's not what.
That's okay. I'm not criticizing it. I'm remembering that there are more things happening in complex variables, several complex variables.
But I'm saying that I think the joint probability nature is already there. The joint elements
could be. I'm not disputing it. Okay. So the main point is, so the entire point is that this thing identically vanishes for all x's. So since this thing vanishes for all x's, for any kind, but we know that the quantum fields, all x's are actually on the vacuum. That is our Hilbert space, full Hilbert space. Okay? So chi is orthogonal to all the vectors of the Hilbert space. So chi is 0, and I have proved the theorem of Rietveld-Steiner. Okay? So this is the proof of Rietveld-Steiner. Okay? So
I'm talking later.
what's the problem?
Where are we trying to show that this phi of x1 actually generate all of it? That's what we were trying to do.
No. It's an axiom of quantum field theory. It's axiom of Weidmann axiom that actually on the vacuum with polynomials for the fields smeared with appropriately. will generate a denser set of vectors in Hilbert space. Field theorem is that even if I restrict the excess in any finite region, no matter how small,
here the excess in this particular equation is general viscosity.
The other one is what the original thing we started from saying that I'm given the left hand side when the excess are restricted to some region. Then I use analyticity in the forward light code to prove that this and some complex variable theory show that this vanishes identically. If all excess excess are not there. Yeah, by analytic integration, all excess in the mu cosine. But then we know that this will generate the full Hilbert space and chi is 0. So there is no such vector orthogonal to everybody. So field theory is proof. So the proof itself is not trivial. At some point, it's not trivial at all. So let me say that this proves that there are no projectors. If a region, bounded region K has a constant complement K prime, it is non-trivial. It is not a point. And you might have observables localized in K and K prime. That means A K and K prime commute. So this is the notation you will come across. This is the algebra generated by AK and AK prime. Yes. So you take AK prime, take the product, take all possible linear combinations and multinomials, and finally also complete in some norm. That is what this symbol means. That is also written as A of K union K prime, and I'll call it A. So this will be a bipartite. This you can, so this A can be factorized in AK and AK prime in this sense. That is given to you if they are causally complementary. The question is, can I also take the Hilbert spaces and factorize it like this? And the answer is no. The reason is the following. The Field theorem says that in K, I take all these monomials completed, I'll get the full Hilbert space. Okay? So that also includes the Hilbert space I get by doing the same thing in K prime. Okay? So the two Hilbert spaces cannot be totally tensor product. It is impossible. So there is no. This already gives the full Hilbert space. So I cannot get anything more by doing the same. I cannot put a second Hilbert space in K prime. It's not there because causality will be violated. So there is no way I can localize states in K or in K prime. Okay? So one consequence of this is this result, which already says also that if a field annihilates the vacuum, it is 0. That a corollary of this result is if you have a quantum field which annihilates the vacuum, it is a 0 field. Why? Suppose phi of x annihilates some vacuum at some. So phi of x annihilates vacuum in some region I'm looking at. You take the monomials constructed from that phi of x, they will all annihilate the vacuum. That will be the full Hilbert space, and you are in trouble. That's not possible. So phi is 0. Okay. So it is a corollary of this result is a quantum field cannot annihilate the vacuum. Okay. It is impossible. It cannot be done. Okay. So let me finish off. It's 3 o'clock. So let me finish up by remarking on partial traces over states and functional figures. Immediately you get into trouble with people doing calculations with partial traces. You get entropies and other things. Partial traces has in the one's head some functional integrals and doing integration over some variables, some subspace of the Hilbert space, but there is no such subspace. So when one does such thing, some principle of quadratic theory is getting violated. Which one I don't know. It depends on the context of the problem, but something is going wrong. So one has to be aware of this fact, and similar criticisms can be applied do many of the calculations with functional layers too. Okay. So it is 3 o'clock. Maybe I'll continue next time. What I want to, but I'll tell you what I want to prove next time. So if I take so, typically the symmetry generator is the integral of the integral of the local density. Okay? So, for example, electric charge is the integral of a local J0 of x. The axial charge is the integral of J0 of 5. Okay? And these are local fees. Okay? These are local fees. What Coleman proved is that if it happens, for example, that any such local charge, any local operator integrated on d cubed x annihilates the vacuum for all time. So it is the symmetry of the vacuum. So there's a J0 should be for a time period also. I don't assume anything more, that it annihilates only the vacuum. Then what Coleman proves is that J0 d cubed x without a vacuum commutes with the Hamiltonian. Okay? That means that it is the symmetry of the whole theory and it is exactly conserved. Okay? For all states of the theory. Okay? So I can replace this vacuum by any state whatsoever in the Hilbert space. This is what Coleman proved. Okay? So if the axial charge integrated annihilates the vacuum, it is a symmetry. Okay? That means it will commute with the Hamiltonian and you will have no pi 0 to 2 gamma, no nothing. Okay? Because it will be a symmetry. Okay? So they will all get forbidden. Okay? So I'll prove this theorem also next time. I think that we can stop here and we can continue this.
That's just what part of that.
Hmm.
Hamilton is not part of that.
H is not a local operator. H is integrated on dq text.
That's the only words for
local operators. Yes. But this theorem will still be true. The statement is K0 dq text integrated vanishes from the vacuum. Then this integral commutes with the Hamiltonian. So the Hamiltonian is integral of T00x. It annihilates the vacuum. So I will be saying that X should commute with itself. But that is true. Okay?
I'm not talking, this J00, for example, J0, for example, and
J0, I don't see that. No. The integral. J0 density, no. Density for sure doesn't annihilate the vacuum. It will create particle antiparticle pairs and junk. It's only after you integrate that happens. So what Coleman proves is that this equation implies that this operator is acting here commutes with the Hamiltonian without any supporting vector on the right. Okay? So it is an actual symmetry of the vacuum. Okay? And other theorem which I will prove is that if you take any local operator and integrate on dq text and act on the vacuum, either it is 0, so it is symmetry, or it is divergent. Okay? So an equation like this, either it is 0 or it is infinite. And this is a theorem due to Fabry and Picasso. I'll show that also. Okay. This is also a fairly surprising result. Okay. So there are no two. Vacuum is carrying all this information. I'll show this to you next time. Then I'll continue it with Professor Sorkin's experiment, law, which he proposed in quantum field theory on how there may be causality violations in experiments in quantum field theory and how it was finally resolved by these people doing algebraic quantum field theory. I'll describe that to you as I keep. Okay.